line, you've got a second virtual machine. And there are not so many parsers available to parse the bytecode, partially because of that. That's a brief excerpt from the manual. It says, section primitive data types. Here, the variable length encoding for unsigned 30-bit uses 1 to 5 bytes. If the high bit of bytes is set, then the next byte is also part of the value. So you've got expanding bytes. It goes on like that throughout the manual, which is, it's not really difficult to understand after all. It's not difficult to implement, but it's, well, it's slow to implement, if you know what I mean. Then there is a very important function or functionality, which is a load bytes functionality starting from Flash 9, which is a load bytes. It's possible to load arbitrary bytes from external sources, from internal sources, packed into the Flash file and modify it any way you like, byte-wise, and then load it into the interpreter. And that's basically a very, very neat way to implement obfuscation techniques. We'll talk about that later on. But first of all, our main objective would be to analyze Flash files. You've now seen approximately what the Swift container format looks like, so I'll go to the analysis. The very obvious method to use for analyzing a Flash file would be to just run it. You start the player, you run it. Has anyone actually switched off Flash in the browser here? Please raise your hand. Oh, it's like everybody. Okay, has anyone left it switched on? It's, okay, like a third maybe. Okay, each and every time you run the Flash file, you're basically doing a runtime analysis, even if you're not actually analyzing it. But, well, usually you would do that in a very contained environment where you can see how it's actually working. But we'd like to prevent that in the first place and know what we're executing, so we try to stick to static analysis here. And the very obvious pattern matching method is what's approximately like the data definition for virus scanners looks like. You know what might be a malware or a Flash file you don't want to execute in your browser, so you're searching for patterns that you know in advance. You could also check for strings in URLs, strings in constants, or inconsistencies. For example, there is the data type of a string in Flash, and the string may be null terminated, and in addition have a length value associated. They might not match, so that would be an inconsistency. Or you've got an end tag where the Flash file is supposed to end, but there might be arbitrary data behind there. It's another inconsistency, and we can search for that. It's a very simple pattern matching. However, when designing your payload or trying to hide your payload, you might know that we're searching for these anomalies and just not use them. So the next obvious choice for an analysis method would be a statistical approach. Here we go. So, like most statistical approaches, it's not really difficult math. It's mostly about counting things. You can count functions, for example. You could count the occurrence of functions and compare it to a reference set. Or you can count the tags and compare it to tags usually being used in your reference set. And then get an approximation to what might be worth executing, what might not be worth executing. Of course, not 100%. It's always like a spam filter. You might get lucky or not. Of course, it's possible to analyze constant names. For example, the constant name next ID or variable name next ID is much less likely to arouse suspicion than something else. Of course, in order to apply statistical methods, we need lots of Swift files to analyze as a reference set. So, the method we chose in this particular instance is a statistical classification for ABC bytecode, which is basically based on n-grams. Has anyone heard about n-grams? It's a very, very common technique. I'll explain it anyway. If you've got a set, for example, the most common application would be a language detection. You've got a text, which happens to be test text here, and the n-gram with n equals 3. So you've got sets, TES, EST, ST, blank, blank TE, and so on, and you count the occurrence of each group. The occurrence of each group here is 1, which is very simple. Now, applied to opcodes, that would mean, for example, you've got opcodes push, push, add, return, n equals 3, so you've got 2 groups, push, push, add, return. Each occurs 1 time. Normally, you would have a lot more opcodes, so the statistics wouldn't be that simple. As a matter of fact, it's not even possible to apply statistical classification properly on very, very few data. So, what exactly would be contained in n-grams of opcodes? And we thought about that a bit, read a few papers. Very interesting read is Supporting the Cybercrime Investigation Process, Effective Discrimination of Source Code Authors Based on Byte-Level Information, which happens to be a paper. And they are describing this n-gram statistical classification method for other languages, not for Flash specifically, but it can, of course, be applied. And the information included here is information about the IDE. You can gather information about the compiler, standard libraries being used, and of course, as each programmer has their own methodology or way of programming, you get information about the author or authors. This very simple graph shows statistical profiles created by the n-gram statistical classification. Each node is one profile, and it shows the distance between Swift files based on the statistical classification method. And as you can see, 2 groups cluster. 1, 2, and a little group down there. So we can assume that these are somewhat related based on the opcode n-grams. Are there any questions so far? Yes, please.
Maybe I missed it, but what is the exact classification method that you're using there? Is it the n-grams?
Yep. As a matter of fact, it's only I'm creating. What I'm creating here is. Sorry.
Repeat the question. What is the metric?
Yeah. What is the metric? The question is, what is the metric or the method? And we're generating the profiles, n-gram profiles, from Flash opcodes, and then compare it to each other. The exact method is described in the proceedings paper. So if you're searching for a mathematical formula, it's written in there. It's also the very same formula used in this paper referenced. So what we get in the end is an approximation which flash file might be related to other flash files. So for example, if we had a reference set, the reference set is all these but not this one, and we'd be analyzing this particular flash file, we would associate it with this cluster, not the other one. It's as easy as that. And one cluster means it's more likely to be of like the reference set, and a different cluster means, well, it's less likely to be like the reference set. Of course, it's not 100% foolproof, and that's what we're trying to prove now. Well, first of all, the classification method can mostly be used only for ActionScript 3 based files. But I'll present a brief history of obfuscation based on ActionScript 2 as well. So when you look at it, you can read the variable a, second line, adds up to a function name, which is loadvars, and the function name is being interpreted as the real function name. So when analyzing bytecode, it's not easy to use pattern matching for loadvars, because you don't know that it's going to be loadvars in the end. So that's a very, very common obfuscation method for ActionScript 2 based Flash. Another very common method is what we call a branch offset obfuscation. You've got at least 2 tags in the Swift file. The first tag has an unknown header, so we don't really know what it is, or it could have a header for a JPEG image or just arbitrary data. But as a matter of fact, there is our secret code embedded in here. And then we've got a do action tag, which is supposed to be real bytecode and just jumps out of the tag somewhere else. Very simple obfuscation. And when you try to analyze it with a common analysis tool like Flare, you end up with this, which is basically garbage. But you can see that it's being obfuscated because it looks a little odd. Then, when we're trying to obfuscate ActionScript 3 so that it cannot be detected even by our classification method described earlier, the very first idea that comes to mind is we just take our payload, which is called NTU here, and we embed it into another Flash file so that most analysis tools would not recognize it as valid Swift in the first place. But it's very, very easily detectable, and it's being loaded during runtime into the byte array here, the NTU byte array. Unfortunately, it is detectable very, very easily, but the byte array idea gets to the next step, and the next step would be this example. The code is written in hex code. Hex is an open source Flash compiler. So the whole process here would be to take our payload, we may even encrypt the payload and then encode it into a byte array, which is being loaded as another class in the data here, which is red. So we iterate over the data, and during runtime we can decode it or deobfuscate or decrypt it even, or implement whatever algorithm we like, which happens to be -1 here in the example, and then we can load our bytes and execute it. Goodbye. There are a few different types of data to hide. First of all, we may have a particular payload to hide. Then we need to hide our encryption algorithm, which could be arbitrary, and we need to hide our encryption key, of course. And we need to hide our encoding algorithm, which is totally different to an encryption algorithm, and parameters may be provided.